Welcome to my presentation. Welcome to the ICEGE 2025. So my presentation title is Integrating AI, Artificial Intelligence, and the Simulation for Smart Energy Systems, and also the Sensor Intelligence. I'm Alan Wang, associate professor in Auckland Bioengineering Institute and also Faculty of Medicine and Health Science at the University of Auckland. The outline of the presentation include the following parts. The first is the brief introduction, followed by the anomaly detection for the sensor signals. So based on the anomaly detection, we will introduce the research work in predicting analyte concentration from electrochemical at the sensor signals. After that, I will introduce the recent work about the simulation of integrated wind and tidal renewable energy systems, followed by some discussions and also the future work and the conclusion of this presentation. The sensor signals. Regarding the sensor signals, we know that they are widely utilized, including the IoT, Internet of Things devices, medical instruments, environmental monitoring systems, as well as the electrochemical sensor signals, which will be introduced in today's presentation. But in terms of the analysis technologies, actually the machine learning and also the artificial intelligence technologies can be widely utilized in analyzing the sensor signals. It's very important to analyze the sensor signals because this will help us to automatically extract the meaningful insights and make the data-driven decisions. So this kind of process can help to improve the efficiency and also can improve the reproductivity. But the traditional signal analysis method, there are several obvious limitations. For example, it's common that the manual feature extraction are utilized, and also the rule-based algorithm is also commonly utilized. So this is quite time-consuming, and based on the limitation of the manual feature extraction, as well as the rule-based algorithm, it's prone to some errors, and it's unable to handle large volumes of sensor data because of the limitation of the rule-based algorithm and also the manual feature extraction. In contrast with the fast development of the technologies of AI and in different areas, so I will think about that some AI or machine learning technologies can be potentially utilized in the sensor signal analysis, especially for example, the supervised learning and the unsupervised learning, and also the deep learning algorithm. So this kind of machine learning and AI algorithm can be utilized to uncover the hidden patterns, anomalies, and also the trends. With the incorporating of large language models, we can even improve the user interactions between the data analysis results and also the report or the analysis results presentation. So in my opinion, the machine learning models can be widely utilized in sensor signal analysis. But besides that, the recent large language models can also be incorporated to improve the interaction. There are a lot of benefits for the intelligent sensor signal analysis. For example, it can improve the accuracy and scalability, which is very important, and also adaptability to the changing data patterns. So we can easily adjust the model trained on one data set or the open set data set to our own data set. And also the ability to handle very complex and high-dimensional data sets. So this is the advantage of artificial intelligence in sensor signal analysis. So the sensor signal analysis, I think the most common problem for the electrochemical after sensor signal analysis, including uh, two major research problems. One is the anomaly detection. The second is to predict the analyte concentrations. So the electrochemical after sensor signals is very potential in offering a very sensitive and selective means to detect the target analytes by utilizing the specific binding properties of aptamers and the electrochemical transduction principle. So I will introduce some recent work done in our group in this area. So this is the schematic of the sensors. So aptamer analyzer as shown on the left figure. So by utilizing the electrode, we can obtain some measurements and obtain the key metrics regarding the different electrolyte and also the measurement of the electrode. So in this study, we have collected three data sets as shown on the table on the right side. So this is the sensoring or protocols utilized in our study. So on the right side, three typical time series data were demonstrated so that you will have a feeling what the data will look like. I think this is the general appearance for the sensor data. Regarding the anomaly detection, uh, so the basic definition for the anomaly detection in sensor signal processing, I think is commonly utilized. So we need to make sure that the data we acquired are reasonably representing the objective we want to achieve. So interpreting an abnormal signal, if we don't remove them, actually can lead to making a high-risk decision. So in terms of the sensor application, so we need to remove this kind of abnormal signals before applying machine learning or deep learning algorithm to perform the intelligent analysis. So how to remove the anomaly detection? Remove the anomal data by utilizing the anomaly detection. The deep learning algorithm actually are very effective. So we will show some results based on our experimental comparisons. The deep learning are quite effective for the anomaly detection, especially the capability for deep learning algorithm to handle the imbalanced data set, which is very common in real world. The semi-supervised learning approach was proposed in our group to address the diverse and unknown features of anomalies and utilize the normal data for training the deep learning neural networks, and autoencoder-based prediction models were then developed to automatically detect anomalous data. The three after sensors were utilized and with the variations in the signal's length for the particular concentrations analyzed and also bioreceptors. The prediction model utilized the autoencoder networks and also the kernel density estimation method has been utilized to find the threshold to detect anomalies. Autoencoder networks include the vanilla, unidirectional long short-term memory, and also the bidirectional LSTM were utilized. And decision-making, the final decision-making was based on the result of the three networks. And the integration of, we tried the integration of vanilla and LSTM networks resulted to compare the performance. So this figure showed the flow chart for the automatic anomaly detection. So basically, we utilize the autoencoder-based neural networks. So the input data is the sensor signals. So we need to perform some pre-processing. So after that, we perform some data augmentation, and then followed by the data split into training data as well as the testing data. For the training data, we design the autoencoder and train the autoencoder. So based on the autoencoder prediction model, we can reconstruct the data, and by comparing the reconstruction error, utilize the mean square error, we can determine the threshold using the KDE. Then if the mean square error is above the threshold, the predefined threshold, then it will be classified as abnormal. Otherwise, it will be normal. So the autoencoder, when we test this, we're using the test set, which is unseen data, to again, we can reconstruct the data, and which is utilized, the testing data is utilized to perform the model evaluation. Again, we can calculate the mean square error. So this figure demonstrates the differences between the normal and abnormal signals from 35 more Australia data set. So the signals for the figure A is the signal with normal sensory behavior, and a signal with abnormal time point. So sometimes it's very common actually when we collect the data, there could be some abnormal time point. So the B subfigure B will demonstrate the some abnormal time point. For example, in A, B, C, and D, in red capital in subfigure B, you can see there are some spikes. So this kind of spikes are abnormal. So we need to detect and then remove this kind of abnormal measurements. And subfigure C containing also some abnormal, but this time this abnormal is abnormal time interval presented in the pink square area. You can see there are some significant jump in the measurement. So the subfigure D demonstrated the abnormal time series registered by a broken transistor. So because of this issue, you can see the data also looks quite abnormal, especially by comparison with the subfigure B, C, and D with the subfigure A. So the prediction models employed will utilize the autoencoder networks and also the kernel density estimation, and the decision making will utilize the different networks. So the performance of the vanilla, this is our finding. The performance of the vanilla and the integrated models were comparable. Basically, they were comparable. But the LSTM, long short-term memory-based autoencoder models demonstrate the least accuracy. Considering the integrated model of ULSTM and vanilla autoencoder, the accuracy for the data with the lengthier signal, the longer signal, was approximately 80%. So the finding is that our proposed model can automatically detect abnormal data, especially when there is sufficient normal data for training. So the nanomaterial-based apt sensors are very useful devices because they can detect small biological species. So this is the beauty of these apt sensors. So to determine the suitable signal processing method, it's very important because the processing method, the proper signal processing method, can improve the identification and the quantification of target analytes detected by the biosensor, and then consequently, so it can improve the biosensor performance. We propose a new data augmentation method and also the long short-term memory to predict the analyte concentration. So the second question is, in order to find the optimal neural network, or we perform some alterations for the following variables. For example, for the long short-term memory, the Lego structure, it could be unilateral, unidirectional LSTM, and also it could be bidirectional LSTM because it's BLSTM. Regarding the optimizers, there could be different optimizer, Adam and IMS, PLP, etc. And also the hidden units and augmented data. So we proposed a new data augmentation scheme, which is really based on the existing reliable data. Then we can generate as many augmented data as we required. This is the experimental results as shown in the figures. Then the machine learning prediction models, we utilize the LSTM, this is the background, then this is LSTM, the architecture, and also we utilize in different our variable settings, for example, optimizer, the hidden units, and also the different data set. This is our prediction model and also the evaluation. So on the left side is the original signals utilizing the ULSTM and then the bidirectional LSTM. And also after data augmentation, this is the experimental result and also the comparison. This is another data set, 35 more. So the evaluation of the neural network revealed that the highest original data accuracy can be increased from 50% to 92% by utilizing the data augmentation method. So it's obvious that for the limited data set, the data augmentation can really increase the prediction performance to improve the generalization capability of the neural networks. In comparison of the optimizers, our experimental results demonstrate that Adam and the RMS prop is more accurate than SGDM. Regarding the unidirectional and bidirectional LSTM, BLSTM, bidirectional is more suitable, especially for the longer time series. So the experimental results demonstrate that the proposed method can automatically detect the analyte concentration from the sensor signals, and the BLSTM is more suitable. This is our recent development by utilizing the deep learning models and also the variations of the deep learning models and integrate them together to perform the abnormality detection. So this paper this year was selected as the best paper award in bioengineering for all the papers published in bioengineering in that year. So it is a very nice recognition for this deep learning models for the abnormality detection in sensor signals. So basically, we developed 7 deep learning classification models, and then in order to identify and quantify the specific concentrations. And the experimental results found that the pre-processing method is very important, which can improve the detection accuracy. So I will use several minutes to introduce our network to integrate the simulation technique for the wind and tidal renewable energy system. We know that the wind and tidal renewable energy system is very important, especially in the pursuit of sustainable and clean energy solution. So we propose to utilize the modeling and the simulation to evaluate the performance. So we designed an integrated offshore structure which capable of supporting a hybrid assembly of 1 wind and plus 2 tidal turbines. So the Cook Strait in New Zealand is the ideal location for wind and tidal renewable energy. Then we utilize the finite element model to perform the analysis and using the optimum G3 to perform the analysis. This is the setup for the hybrid system, consider of both wind and tidal turbines, and the finite element analysis is utilized. This is the experimental result by applying different parameters. So the experimental results demonstrate that the monopile has been found to be the very suitable foundation type as the most inexpensive solution in water depths less than 30 meters. This is our finding. So this result enables the finding of the amount of deflection for each soil type, and also the maximum deflection of the structure occurs for firm clay soil in rotational speed of 11 to 13 RPM. This is our finding, which is published in Geoscience. So now come to the discussion and conclusion of my presentation. So the simulation offers a cost-effective and time-efficient way to test the hypothesis, as shown in the tidal energy simulation. And then the enhanced signal analysis capability utilizing machine learning and deep learning algorithm actually can be very important and even revolutionize the field of sensor signal analysis. So improve the decision making and problem solving by extracting valuable insight from sensor signals, and also leading to informed decision making, early detection of anomalies, and also it's very effective actually to solve the real world problem by utilizing the sensors. So integrating the simulation and the intelligent sensor data analysis has numerous advantages. Can improve the efficiency, reduce the cost, etc. So the application of simulation and intelligent sensor data analysis offers a lot of opportunities for innovation and advancement. For the future prospects, I think the integration of the advanced machine learning and deep learning algorithm, as well as the large language models, can increase the automation and also friendly user interaction, especially it's also very important to incorporate the domain-specific knowledge. So the collaborative effort is always needed because the interdisciplinary collaboration between researchers, engineers, and domain experts can drive further advancement in simulation and sensor signal analysis for shaping a smarter and more efficient future. Finally, I want to thank our collaborators in different projects and also the funding agencies. Thank you.